Hello, in this video we will talk about the topic of universal gates. First of all, we'll start introducing other logic gates, the NAND, NOR, and the XNOR gate. Next, we will talk about common Boolean properties that will help us later on when explaining universal gates. The two universal gates that exist are the NAND and the NOR gate. We will talk about this in details later on. And finally, we'll talk about how we can design basic logic gates using the universal gates, and finally how to implement a logic expression using universal gates only. The NAND gate is short for not AND. So basically, you take the output of the AND gate and then invert it, and that results in the NAND gate. The symbol for the NAND gate looks like the AND gate, but with a circle at the end of it, as you can see here. So the circle indicates inversion or complementing. You can express the NAND gate as a Boolean expression as A and B with a bar on top, because the bar means inversion, or the bubble actually. Here. Another way to express it is to put a bracket. Inside it we'll put A and B. Outside the bracket we will put an apostrophe. On the trainer board, the symbol for the NAND gate looks like the AND gate, but you will take the second output, which is the inverted one. The NOR gate is short for not OR, and the output is simply the inverse of the OR gate output. Here you see the truth table of the NOR gate. It's exactly like the OR gate truth table, but the opposite. So whatever value you see at the output of the OR gate, you invert it, and that will give you the output of the NOR gate. The symbol for the NOR gate looks like the OR gate, but you have a circle at the end, which indicates inversion. As an expression, or a Boolean expression, you can write A nor B as A or B, but with a bar on top of it. Similarly, you can write A or B in between brackets and put an apostrophe at the end to indicate that this is the NOR gate rather than the OR. On the trainer board, you will take the second output, which has a circle at the end of it, because this is going to be OR with an inverter, which is actually not OR, or NOR gate. The last gate we'll introduce today is the XNOR. It's actually short for not XOR. And the output of it is the inverse of the XOR gate. If you remember, the XOR gate outputs a 1 when we have an odd number of ones at the input. So the XOR gate, if you invert the output of the XOR gate, you will get an XNOR gate, which gives you an output of 1 when you have an even number of ones at the input. The symbol for it looks like the XOR gate, but again, there is a bubble at the end to indicate that you're inverting, or to indicate that there is a bar on top of the expression. So the expression for AX or B, or the expression for AX nor B, is AX or B with a bar on top of it. Or again, we can put AX or B in between brackets and put an apostrophe at the end for the XNOR gate. Let's introduce some Boolean properties. First one we'll cover is the complementing twice property. Remember that the inverter simply inverts the value of the input. If you give it a 0, it gives you a 1, and vice versa. So if we complement a variable twice, that means we will get the original variable back. That's the first Boolean property, and we can express it in a logic diagram as such. We have two inverters connected in cascade mode like this. The first input is A. The output of the first NOT gate is going to be A bar. The output of the last inverter will be A, because we're getting rid of the complement here, right? The second Boolean property we'll introduce is De Morgan's law. De Morgan's law states that we can distribute the complement on A or B, or in this case, it's actually the entire expression is A nor B. We can distribute the complement on each of A and B, but this will convert the ORing into ANDing. Okay, so we distributed the complement and we changed the OR into AND. So this is useful if we want to get rid of the plus sign in any expression without changing the expression. We can simply complement twice by using the first rule and then distribute only one of the complements, which will take care of the conversion of the ORing into ANDing. Okay. De Morgan's law can also be applied on NAND gate. So if you have A NAND B, you can distribute the complement on each of A and B, and this will convert the ANDing into ORing. Okay. There are other Boolean properties that are very common. First, the first list here deals with the AND gates. If you AND any variable with 1, the output is that variable. Because remember we said ANDing is kind of similar to multiplication. So any number multiplied by 1 gives you that number. The second property is ANDing with 0 gives us a 0. You can think of it as multiplication because any number that's multiplied with 0 gives you a 0. Or, since the definition of the AND gate states that all the inputs must be 1 for the output to be 1, here you have one of the inputs being 0, so the output must be 0. The last property for the AND gate states that ANDing A with itself gives us A. Because you can try different examples, for example, 1 and 1. 1 and 1 gives you 1. There are only two scenarios. 1 ANDed with 1 gives you a 1. A could be 0, so it will be 0 ANDed with 0, which is 0. So no matter what value you have for A and A is always equal to A. The second set of properties we'll introduce have to do with the OR gate. So A or 1 gives you a 1. Again, you can look at the definition of the OR gate, or you can think of this as addition. Or remember, OR is equivalent to greater than or equal to 1 on the trainer board. Okay? ORing any variable with 0 gives you the original variable back because you're simply adding a 0, which doesn't have an impact on the expression. The last Boolean property is A or A gives you back A. Again, you can experiment with the two cases, A being 0, so 0 or 0 is 0. A could be 1, so 1 or 1 is actually 1. We will come back to the Boolean properties in the future slides, but let's now introduce universal gates. Universal gates are actually gates that can be used to build or implement other gates. There are only two universal gates, the NAND gate and the NOR gate. Now we'll study how we can implement a NOT gate or an inverter using NAND gates only. We'll start with proving this algebraically and then look at the final circuit schematic or logic diagram for the expression. Remember this rule we saw earlier that states that A and A is equal to A. So I have A written here. I have expanded it into A and A. Next, what I'm going to do is complement both sides of the equation. All right. So that means A bar, or not A, is equal to A NAND A. So now what I did is I designed an inverter gate using one NAND gate whose inputs are connected together. So the NAND gate can at least take two inputs. And to implement an inverter or a NOT gate using NAND gates, I will short the two inputs together, connect them like this, and then connect them, use these as the input of my inverter. Then the output will be not A. So what we have now is actually an inverter gate made using NAND only. This is A bar. Next, we will learn how we can implement an AND gate using NAND gates only. Remember, we said that the NAND is actually not AND. So what we need to do is simply get rid of the NOT to get AND from NAND. So we can connect the inverter we made earlier at the end of the NAND gate. So we can do this directly through schematic, or we can show the proof on how to make it. So we can write y is equal to a and b as an expression. And then I will complement this twice because this is property number 1 that we learned. Next, I will expand this into a NAND b NANDed with a NAND b. Okay. Now, what I have here is a and b written in terms of NAND gates only. This is the NAND gate. This is NAND gate acting as a NOT gate. So I have NAND with NOT, which gives me back AND at the output. The third proof we'll look at is how to implement OR gate using NAND gates only. We'll start by writing the expression for the OR gate, y is equal to a or b. Next, I will aim to get rid of the OR and replace it with AND. And we learned that De Morgan's law can help us do that, so I will apply property number 1 with De Morgan's law. The first property says that complementing an expression twice gives me that back the original expression. Okay, now I will distribute the bottom complement, this one, on both A and B, and that will change the ORing into ANDing, and it will distribute the lower bar on each of A and B. Okay, I want to write this in the form of NAND gates only. So I can expand A into A NAND A. I mean A bar into A NAND A, like such. Okay, because one of the rules we said earlier is A is equal to A and A. This is what we did here. I expanded the A to A and A. Now what we see here is an expression written using NAND gates only that acts as OR gate, as an OR gate, because that's where we started from. And this is equivalent to this part of the expression. Sketching this will give us 3 NAND gates connecting in this way. The first one acts as a NOT to give me NOT A. The second one acts as another NOT gate to give me NOT B. And here, this NAND gate is actually taking NOT A, NOT B bar, which if I apply De Morgan's law is going to be equivalent to A or B, which is what I am looking for. Now we'll do the same thing but with NOR gates only because it's our second universal gates. I will just skim through this because we're basically applying properties to do that. So A is equal to A or A. This is one of the rules we looked at earlier. And then I will complement both sides. And now I have the final answer for how to implement NOT using NOR. Next, we'll look at the OR gate and how we can implement it using NOR gates only. I'll write the expression first, complement it twice, and then rewrite it in terms of all NOR gates. So A NOR B, NORed with A NOR B. All right. You can think of this as x or x, right? Which is equal to x. So I didn't change nothing yet. All I did is I rewrote it so that it looks like it is consisting of NOR gates only. Sketching this will give us two NOR gates connecting this way, and they're both acting as A or B, or as an OR gate. The AND gate can also be implemented using NOR gates only. For the proof, we will write first y is equal to A and B. I will complement the expression twice, which shouldn't change anything. Then I will distribute the lower complement by applying De Morgan's law. And finally, I will expand each of A and B by applying the rule of A or B is equal, actually A or A is equal to A. A or A is equal to A. Sketching this gives us three NOR gates connecting in a way that they're all acting as AND gate, two input AND. Now we'll prove how we can create the XOR gate or the exclusive OR gate using NAND gates only. We're given a hint that A XOR B can be expressed as not A ANDed with B or A ANDed with not B. So we can start from the given hint and then move on to rewrite this expression so that it looks like it has all NAND gates only. I will explain how we moved between steps here, or what rules we have applied, or Boolean properties. Starting from this line, what we did is actually added these two terms to the expression. And if you think about it, A ANDed with not A is simply 0, right? So we didn't change the expression. Also B ANDed with not B is 0. So this is one of the rules. All right. In the next line, we rearranged the expression because A or B, it's like addition, is equivalent to B or A. So only what we did here is only rearrange the expressions such that we put the ones with a common factor next to each other. In the first term, the common factor was B, so I factored it out. Here, the common factor was A, so I also factored it out. Here, what we did is we factored out this common factor again. Okay, here it is. And we're left with A or B, ANDed with the common factor. Next, we complemented only the second term, which is what we factored out earlier. And we said complementing twice has no effect on the expression. From here to here, we applied De Morgan's law by distributing the lower complement on each of A and B, because A bar complemented gives us A, and so on. All right, between here and here, we distributed this term on each of A and B. Between here and here, we complemented twice. Between here and here, we applied De Morgan's law by distributing the lower complement. So this is the final answer that you will see. It's a sketch of the expression we saw earlier. All these four NAND gates, they're configured in a way or connected in a way that they're all acting together, they're acting as A XOR B, or as an XOR gate actually. We can put any inputs here in the beginning, and the output will be the results of XORing them together. Next, we'll look at how to implement XOR gate using NOR gates only. We'll start with where we're left earlier from the NAND gate proof, or how to implement XOR using NAND. If you go back to the previous slides, you will see this being one of the expressions equivalent to A XOR B. So we're starting from here and moving on until we reach the final answer. Between here and here again, we applied De Morgan's law by distributing the lower complement. From here to here, we applied De Morgan's law here on the term on the right side. Between here, or this line and this line, what we did is we distributed A nor B on both A and B. So we ended up with two terms. Next, distribute the bar or the complement on each term by applying De Morgan's law. Up to here it's sufficient, but it looks like we're having an OR gate at the end, right? This is OR. So to convert the OR to NOR, to convert this OR to NOR, we applied two complements, which is equivalent to the original expression. This way we will have NOR gate here, and the top bar is going to be an inverter made using NOR. So the final answer you will get is the following. This is the sketch of the XOR gate implemented using the universal gate NOR. So you will need 5 NOR gates connected this way to get A XOR B, or to get the XOR gate. This slide summarizes how we can implement the basic gates NOT, OR, and XOR gate using universal gates only, whether using NAND gates or using NOR gates. For example, we can implement the AND gate using 2 NAND gates connected this way, or using 3 NOR gates connected this way. All of these circuits, all these 3 circuits are equivalent in terms of functionality or logic-wise. They both have the same output given A and B as inputs, or any 2 variables actually. Now we'll do an exercise that asks us to implement an expression using universal gates only. To be specific, we want to do the expression using NAND gates only. So the first step we will do is sketch the expression on the board using the original circuits, or the original logic gates. First, we will need AND gate to obtain C and D. We also need an OR gate to OR B with C and D. And finally, we need an additional AND gate to AND A with the rest of the expression. All right, so this is the sketch of the original expression. What we will do is, instead of looking at the proof on how to convert the expression into its NAND gate mapping, what we'll do is convert this graphically, meaning each gate we look at, we will replace it with its representation using NAND gates only from the table we saw previously. So let's do one gate at a time. Since we want to do NAND gates only, now I have here how to convert each of the gates that I have in my sketch using NAND gates only. Okay, we need the inverter. I don't have an inverter in the expression, so I will skip this one. We need the OR gate here, right? And so this is the OR gate, and we need 2 AND gates. I'm gonna maybe sketch or draw a tick for each of the AND gate that I see in the expression. Okay, I will start by highlighting all the AND gates that I have, and then highlight how to do them using NAND gates only. Okay, now I will replace each of the AND gates that I see in the circuit with how to make it using NAND gates only. Simply just remove the AND gate and draw 2 NAND gates connected this way instead of it. Okay, this is the second one. Next, I have this OR gate that I need to get rid of and replace it with its NAND gate representation. This is the OR gate. This is how to make an OR using NAND gates only. So I'm gonna replace the OR gate in my diagram with 3 NAND gates connected this way. Now I have everything drawn or sketched using NAND gates only, but it's not in its simplest form. So remember the rule that we mentioned earlier about complementing an expression twice results in the original expression. This rule could apply also on logic diagrams. So the final step we want to do is to eliminate inverter pairs. So two inverters cancel each other if they're connected in cascade mode. And remember, inverters can be made using NAND gates only or using NOR gates only. For example, here, this is an inverter made using NAND. So we have to search for two inverters made using NAND that are connected together. Okay, there's actually one pair, which are these two. So to simplify the diagram, I'm going to cancel these two together and simply replace them with a wire. Okay. So this is the final answer that you will have. We will end up with a total of 5 NAND gates to implement the expression that was given. To eliminate inverter pairs, you have to check whether our diagram has inverter pairs connected in cascade mode. Inverters, remember, can be expressed using NOT gates or NAND gate or NOR gate. So whenever you see any of these in a logic diagram, you can simplify the expression and put a wire instead. Same thing here, two NAND gates that are acting as inverters that are connected in cascade mode, you can cancel them together and replace everything with a wire because the input is A, the output is also A, as you can see here. So you can put a wire instead. It will do the same thing for us. These two NOR gates that are acting as inverters, they're connected in cascade mode, so I'm going to replace them with a wire. So this is a general rule on how we can eliminate inverter pairs in a logic diagram. In this slide, we see a summary of the logic diagrams that we must implement in this lab sheet. In the lab sheet of this lab, we will do these expressions on Logisim as well as on the trainer board. So in Logisim, we'll simply implement these. Make sure you connect input pins for A and B. These are input pins, so they have to be squares. The output pin is actually round in Logisim, and you can label it F or AX or B, whatever. But AX or B is more descriptive in this case. Okay. So this is how to implement AX or B using NAND. This is AX or B using NOR. And this is the expression that we looked at earlier, this one, using NAND gates only. So this is it for this video. If you have any questions, please message me on Teams during office hours or send me an email.